Okay, welcome everyone to the sequencing and pre-confirmation call number 12. Today is demo day. We have 4 different teams doing 4 different demos. I guess before we get started, I just want to give a little bit of a progress update since last time. One piece of exciting news is that there's 2 new base rollups on my radar. Number 1 is a Japanese team called Intmax. They're building a really, really interesting ZK rollup that is specialized for payments, where the on-chain overhead is 5 bytes per transaction. So it's very, very small on-chain overhead, and they're building it as a base rollup. And then there's another base rollup from the Taiko team called Gwyneth. And I'm not sure if it'll be run as 2 parallel chains or if one will update the other, but exciting nonetheless. Another update is that we now have a repo on the Ethereum GitHub organization. So it's Ethereum/preconfs. The role of this repo is basically to host the credibly neutral code, in particular the registration contract, where we really want everyone to agree on one canonical registration contract, which is maximally credibly neutral. So if you do want to work on the registration contract and you're not part of the registration contract Telegram group, do get in touch with me. I guess since last call, we've had sequencing day at EthCC. A lot of people have been talking about pre-confirmations. I feel like the word is really starting to spread out and people are getting comfortable with the concepts. And in addition to doing the education and spreading the word, I think there's been a lot of actual development on testnets. There's a new testnet, the Helder testnet, which is dedicated to pre-confirmations and proposer commitments. And today is where we'll see a lot of these proofs of concepts live. So without further ado, let's start with the very first demo from the Gattaca team. Kubi and Lorenzo, the floor is yours.
Cool. Can everyone hear me all right?
Yes.
Okay, nice. I'm just gonna share the screen.
Share with the screen.
Okay, yeah. Okay, perfect. So hi, Kubi and Lorenzo here from Gattaca. So we mainly focus on infrastructure around pre-confirmation. So we're not actually building a pre-confirmation protocol itself. I guess we have been sprinting towards various improvements since Zoo Berlin. So we're just gonna talk just very briefly about what we've built and then actually run through the demo just to set the scene a bit. Second. Yeah, okay. So if you guys remember back from Zoo Berlin, the main focus there was on inclusion pre-confirmations, which was a very good sort of foundation to work towards actual L2 execution pre-confirmations. And the main milestone there really was that there was some consensus that was reached across different teams to basically make some changes to the existing PBS stack. So across proposer to the relay to builders to actually enable inclusion pre-confirmations, L1 pre-confirmations for that matter, in Zoo Berlin. And this was actually like an important sort of stepping stone to work towards the next stage. And then just this is a quick refresher. Is the notion basically that L1 proposers can opt into being pre-confers. And the proposer can either be the pre-confer themselves directly. So, for example, the BOLD protocol enables that. But also there's this notion that these proposers can delegate the right to be or to issue pre-confirmations on behalf of them. But no matter whether the pre-confer is the proposer themselves or a delegated pre-confer through a gateway, there's basically this notion of a look ahead where even if not every proposer has actually opted in to being a pre-confer, essentially the proposer who's next in line has exclusive rights to issue pre-confirmations during these gap proposers. So just as a quick refresher. And then what we have actually built now on Helder to get to L2 execution pre-confirmations is the following. And so basically you have a pre-confirmation RPC/router, and this is also open source. And the idea is basically that the users or wallets can directly request pre-confirmations through this RPC endpoint. And the router/RPC is responsible for, by looking at the look-ahead, basically identifying who is the right elected gateway, or could be a proposer directly, but essentially who's the entity that can issue pre-confirmations based on the look-ahead, and essentially make sure that these can be issued, and whenever there's a transition, then switch to the right pre-confirm accordingly. And the way we got everything to work on Helder specifically, without requiring any changes on existing wallets, so we actually use MetaMask here in our demo.
Your CI/CD process?
Sorry. Oh, okay. I think that was a mistake. Yeah, so we basically will be able to respond to current RPC calls that wallets already use in order to give the user the same experience that they are already used to without actually requiring any changes on the wallet front, which is actually quite nice because that will help a lot with adoption. And so like some of the standard like RPC calls, like you said, raw transaction, get transaction receipt, transaction count, are basically exposed via the RPC and then redirected to the router, the gateway. And this is important because the gateway actually maintains state and advances state. And so the gateway can actually return the exact correct data at any point, even though the data might not actually be on chain yet, which is important, especially given you have gaps across multiple proposals. But even when you have single proposal or multiple proposals in sequence, you don't want to be constrained to the 12-second block time. And so what the gateway essentially does is it can respond and issue pre-confirmations really, really quickly. So when we are running our demo, we had pre-confirmation responses in the realm of 20 milliseconds or so, which is really, really fast. And then can also provide answers in regards to specific queries on like what the state is, or getting transaction receipts and all those kind of things, which is quite nice. And here we also somewhat separated the role of a gateway from the act of actually maintaining state, just so that the gateway potentially can actually also be operated by entities just like the relay, for example, that actually don't need to maintain all the state and everything. And we'll also open source a version of the gateway that we're working on. And so the idea is basically, as I said before, you have this notion of a schedule, and for that specific point in time, a specific gateway can issue pre-confirmation and maintain state. And as the pre-confirmations are being issued and the number of transactions reaches a certain threshold, the gateway can then basically create these batches and then post them onto the L1. And these can be viewed as L2 blocks, so to speak, and can be included in L1 transaction, actually then enforced when it's actually time for the gateway to, or that specific proposer to build the L1 block. But in the interim, again, they can make that state available. I think there was a question somewhere. Let me see.
The question was, do you guys support L1 preconfs as well?
Just inclusion, not execution. So in theory, you can provide execution preconfs for L1 as well, but that definitely it puts a lot more constraints, and the sequencing itself it changes significantly because there's already a status quo on the L1 and certain kinds of returns that are expected because of the MEV auction. And so if you change that and do everything like on a first come first base surface, that will massively change the rewards, if that makes sense.
That makes sense.
Yeah. Cool. So now we're going to actually show you how this works in practice.
All right. Hi, guys. Can you all see the MetaMask, everything?
Yes. Would you mind clicking hide on the Zoom message that's in the center?
Nice.
Thank you.
So here we have the gateway that's running. And then from MetaMask, I already set up the RPC, so that is going to be routed to the gateway. Yeah. So now the gateway has okay. That was too fast. But so basically there you go. So this is kind of what we think the UX could look like. So the user sends the transactions, and then for a certain amount of time, the Explorer still shows it because the Explorer is connected to the gateway, so it receives this preconf state ahead of time, and then it shows us pre-confirmed. And on the gateway side, we received it, the transaction, and then we sent it to the sequencer for execution. And if you see the timestamp 493, so it took around 22 milliseconds to be sequenced, and then it's ready to be queried by the wallets or the Explorer. And then what happens is that we create these L2 batches, which are right now there was just one transaction, so we created a block with a single transactions, and then that's gonna end up on chain. So after a while, when that's landed on chain, this pre-confirmation will source no, which means that now the L2 block containing this transaction has landed in an L1 block. So essentially now this block enjoys the same kind of L1 guarantees. Yeah, that's more or less the demo.
Okay, super cool. Very, very low latency. I like that. Are there any questions from the audience on the demo?
Is it relatively general purpose? I know you guys were doing it on Taiko layer, I believe that, but I would assume it's relatively general purpose to apply that to any of the different L2 frameworks.
Yeah, exactly. Yeah. So yeah, for this demo now, we worked with Taiko, but we actually also work with a bunch of other teams, and yeah, this is trying to be as agnostic to the L2s as possible.
That makes sense. Thanks.
I am curious about the integration with MetaMask. Can you talk about how that was done? Did you use a snap, or did you mock the blocks or something like that?
Yeah. So this demo now mocks the blocks. I think we discussed this before. We essentially built this in such a way that the gateway is responsible to make state available to whoever needs or wants to have access to state until it actually lands on the L1. So you actually have this nice and smooth transition. Although we also spoke with MetaMask and currently experimenting with developing a snap to have some better UX changes there.
And what are the main next steps in terms of getting towards production in mainnet?
Yeah, so from our perspective, we need to solidify some of this infra, and we're also going to open source a version of the gateway as well. So for now, we only open source the RPC, but we also want to make a gateway version available. And then most of the work is actually around so working with the teams that are working on the registration contract. So we integrate the look ahead that's implemented there, and also things around slashing and things like that. So we integrate that properly, because this is currently in this demo also not enforced.
Okay, fantastic. Thank you so much, Kubi and Lorenzo. Next up, we have the Bolt team who will be talking about L1 preconfirmations.
Yep, let me share my screen. All right, can everyone see that?
Yep.
Cool. So yeah, in this presentation, we also mainly wanted to give an update since our last presentation and our last status at Zuberlin. So let's start with what's new. So obviously we've deployed on Helder alongside an initial registry for proposer discovery. So that's the same registry that Kubi was talking about. We've also deployed a minimal Bolt RPC, which actually also does kind of the same functionality as the gateway in the sense that it provides a translation layer between what language wallets speak and what language the preconf APIs speak, in a sense. It also takes a look at the look ahead to proxy requests, so that's also similar functionality. On top of that, we've been working on local fallback block building. So as you know, we do preconfs on L1, and we are compatible with PBS. So in the case that PBS fails to deliver a valid block, the sidecar will actually build a local block that adheres to all of the commitments so that there's no liveness faults or safety faults that come from a failure downstream in the PBS pipeline. We also added support for blob transactions, so type 3 transactions, and bundles. So you can think Flashbots bundles with relative atomicity guarantees, but alongside you get a pre-confirmation. And we've updated our commitments API, which you can find at the link here. I will share the slides in the Telegram right after. So yeah, let's get straight into the demo actually. So for our demo, we've decided to do an ETH transfer with an L1 inclusion preconfs, showing a possible way to also integrate with MetaMask. We did not go the route of mocking the receipt, and so we took a different approach in that we send a signature request to MetaMask and then send the transaction actually to our RPC. So let's go over that right now. We'll send some ETH to a random wallet. Request a signature from MetaMask, and then we get an instant confirmation. Let me just, it's not as quick as the Gattaca one. You can see it's, goddamn, 132 milliseconds, so not as fast. And it will provide a link to the to be proposed slot. So now we'll quickly wait for it to be actually included so that we can show it was successful. Sorry, this is not easy. Okay. Okay, there we go. So we got a block scout link showing that the transaction was actually confirmed. And then we can go to Dora, the Explorer, and actually see that the block was built by built by Bolt, sorry, with the Bolt builder. So that was the quick demo. And in terms of what actually goes on under the hood, we thought it'd be useful to show an excerpt of all of the logs. So the first thing is that the wallet sends a request, an inclusion request to the sidecar. The sidecar will then read from the look ahead and proxy the request to the correct proposer sidecar. It reads this RPC endpoint from the on-chain registry and then sends the request to that sidecar. The sidecar will then validate the transaction. So it will validate the base fee, the nonce, and the balance. And as soon as it passes the execution state validation, it will respond with a commitment. It will also turn these commitments into the constraints and send them to MEV Boost, which will in turn send them to the relay and the builder. The builder will then store them, and as soon as it is time to start bidding, we'll actually create a multi-proof for it for the constraint proofs and send that block with the proofs to the relay. The relay will also verify these proofs to make sure that the bid is actually eligible for the auction. Then as soon as MEV boost or the modified MEV boost receives the get header with proofs request, it will forward that to the relay, and the relay will deliver the bid with the proofs. In turn, Bolt Boost or Mev Boost will also verify those proofs to make sure, once again, that they're all valid. And once that's done, it will return it to the Beacon client, ready to be signed and broadcast. So yeah, that was a quick demo. In terms of next steps for us, kind of divided into research and development. So on the research side, we're really looking a bit deeper into all of the potential use cases and also potential economic modeling and a bit of forecasting, like what would this benefit proposers who choose to run this? What do penalties look like? So slashing and freezing, these are problems that are being widely discussed as well. Fair exchange is an interesting one. Currently, we kind of use the RPC, the Bolt RPC, which sits in the middle as sort of a timestamping oracle, which can timestamp requests and responses and make sure that these responses actually happen in time. And in case a user is not happy, they can go to the RPC and request like some evidence of misbehavior. And we're also exploring other commitment types. So Bolt in general is a proposer commitment protocol, of which inclusion precons are a very good example of, but there are potentially others that are very interesting. We want to move to Holinsky by the end of September. But before that, on Helder, we first want to finalize a couple of things. So the commit boost integration, we want to make sure that's very streamlined, provide easy ways for validators to run these sidecars through commit boost. Also integrate their signing manager for extra security. We want to collaborate on the registry implementation, which is not finalized yet. There are a lot of open questions there. And also, obviously, it's a topic that needs a lot of scrutiny because the security depends on it. And then we want to finalize the constraints API, which is how the Bolt protocol interacts with the PBS pipeline to communicate constraints and verify proofs. There is also a discussion going on GitHub in the link there. And then finally, yes, we want to move to Holinsky by the end of September with a more streamlined MVP that implements things that come closer to an actual production deployment of proposer commitments and inclusion precons on L1. So that was it. Thank you. If anyone has any questions, I think we have time. Oh, okay. No questions.
I have one. I saw you guys added bundle support. How is the bundle support working? Are you guys like essentially simulating the bundles and then essentially you're guaranteeing atomicity at the time the request is made, but the atomicity could be broken by a later request? Is that kind of how it's done, or how are the bundle support done?
Yeah, so we provide atomicity not in the sense that actually, yeah, I made a bad analogy. So in the sense of flashbots, you get atomicity on execution as well. We just provide a guarantee that your bundle will, if it's included, it will all be included in the same order. But one of the transactions could actually fail because we don't provide you with execution guarantees. We only provide you with inclusion guarantees. So it is strictly just an extension of inclusion precons. And yeah, the execution guarantees are not implemented. So that was a mistake on my part.
Okay, that makes complete sense. That's kind of similar to the guarantees you get round shared sequencers then in bundles.
Got it. Okay.
Did I understand correctly that the pre-confirmation notification happens at the app layer, not at the wallet layer?
Yes. So in contrast to the previous demo, we couldn't get the mocking working. So for now, we use sort of like a more of an intent structure where we request a full signature from MetaMask and then actually forward the full signed transaction to our RPC using send raw transaction. And then we use that response to create this pop-up that you saw on the front end. But since the signature is requested from MetaMask and not actually sent through the MetaMask RPC, we don't get a confirmation inside of a MetaMask. And we are also thinking about how we can potentially improve that because the UX is obviously not great, and MetaMask actually gives you a warning when you try to sign transactions, which makes sense. So we're also looking at snaps and various other options.
Are you guys also looking into L2 pre-confirmations or mostly focusing on L1?
So mostly focusing on L1 right now. There is in the research, there is some overlap, which I think is great because we can tackle the problems for both L1 and L2 at the same time, or at least the ones that overlap. Where we do overlap is like some other protocols might rely on forcing inclusion of a sequenced batch, and that can be done through Bolt. But we are not focusing on the actual sequencing and pre-confirming of L2 transactions.
And can you briefly talk about the other commitment types that you guys are looking into?
Yeah. So I think one that I find interesting is sort of a block space claim type of commitment where you can get some sort of block space reserved for you in advance, even though you don't necessarily know what you're going to put in it yet. So this can be useful for protocols that want to offer things like gas futures and stuff like that. We've just started doing some research on that, so it's not that there. Obviously, the fair exchange problem is very much more outspoken in that situation because the user gets a signed a commitment for a sort of block space claim, but then actually has to deliver that payload. So it's similar to the PBS fair exchange problem. So it's kind of a more difficult commitment type, but we're definitely interested in figuring it out.
Okay, thank you so much. Any other questions from the audience before we move on to the next demo?
Cool. Thank you very much.
Jonas, thank you so much. Next up, we have the Switchboard team. From
Yeah,
Nevermind.
Can you hear me?
Yes.
Okay, cool. Okay, so this is a Taiko pre-confirmation demo in Helder testnet. We are Switchboard, a subsidiary of Nethermind, focusing on pre-confirmation, research, and engineering. Next slide, please. So this work is in collaboration with and funded by Taiko. Oh, previous slide. Yes. And so a huge shout out to Taiko. Next slide. And huge shout out to the team, Ahmed, Anshu, Marty, Mikael, Smoltnil Corner, for making this all possible. I am Leno Shitani presenting. Next slide, please. So first, let me give a design overview of what we are implementing. So the POC design, our POC design works as following. First, we split each 12-second L1 slot into three, for example, 4 3-second subslots. And at each end of each subslot, the pre-confer, who is elected from the opted-in L1 proposer, will build, sign, and publish a Taiko L2 block to the network. In other words, they're pre-confing the whole L2 block. Next, Taiko users will listen to these pre-confed L2 blocks to know the result of their L2 transaction without waiting for the L1 inclusion of their transactions. Next slide, please. So here's a sequence diagram of what I mentioned. So first, the L1 proposer will call an L1 contract to register as a pre-confer, so they opt in. Next, the L1 contract will have an election mechanism to choose who the pre-confer for that slot should be. Now next, when the L1 proposer, it comes to the L1 proposer's turn to actually be elected, what happens is that first, the users will submit L2 transaction to the Taiko network, specifically to the Taiko mempool. Next, the L1 proposer will fetch these transactions from the Taiko mempool, locally build and signed an L2 block, then propagate the signed L2 block to the Taiko network. Next, the full nodes that are listening to these pre-confirmed L2 blocks will execute the L2 block and provide the user the latest pre-confed state. Now this whole round will be iterated several times within one slot. Now at the end of the slot, the proposer will submit an L2 block to the L1. And then the L1 contract will check if it's like the expected elected preconfer and accept it. And then later on, a distributor who's like monitoring the network can look at the preconfed L2 block and the L2 blocks that were actually submitted at the end of the slot and provide fraud proof if they contradict with each other. Next slide, please. So like one of the unique features of our POC is that it implements batch preconfirmations. What I mean by batch is preconfirmation is that we provide preconfirmation at a batch level. So here at the L2 block level. For example, this is what Optimism provides with their 2-second block times. On the other hand, there's continuous preconfirmations where the preconfer provides preconfirmation at the transaction level in a continuous stream. For example, Arbitrum provides this. Okay, next slide, please. So why do we batch? So the issue with continuous preconfirmation is that it is hard to incorporate a pricing mechanism. This is because the preconfer needs to decide to preconf a transaction just by looking at the single transaction and a tip or a very limited number of transactions. Now, lacking a pricing mechanism is an issue because first, the searchers in the network will optimize for collocation network latency because the faster you reach the preconfer, the higher chance of inclusion you have. So there will be a latency race. This means that value is not captured by the tip, but it's rather leaking out of the system in terms of like these collocation costs or these like network costs. Another issue is that searchers might just like choose not to participate in this latency race and just spam the network L2 block with probabilistic arbitrage transactions. So as a result, this drives up the fee for end users because the L2 block will be filled by these transactions. So if you look at like the ultra low latency blockchains and rollups that you see right now, like Arbitrum, Polygon, and Solana, they all face this latency race and these spam issue. So the nice thing about batching is that batching enables pricing via auction within the batch. So by being able to run an auction, this mitigates latency races and spam because the searchers will be incentivized to participate or like express a preference in terms of tips rather than like paying for the latency, like reducing the latency or collocating or like just spamming the network. And another nice thing about batching is that opens doors to PBS for these pre-confed L2 batches or blocks. More on this later. However, we do lose speed of light latency pre-conf service, for example, seen in the other demos. So we'll be like 2 seconds or 3 seconds latency. Okay, next slide, please. So that is it for the design part and the reasoning of the design. Next, Archie will present the demo of what we did for Helder.
Yeah, thank you, Lin. So at the beginning, I want to give you a few words about our AVS node, which you can see in this diagram in the center. This is our core component, which is responsible for interacting with Taiko clients, so Taiko proposer and Taiko driver. What's more, it has its own dedicated peer-to-peer network, so AVS nodes can share information about preconfirmations. It also calls L1 smart contracts and used modified Mev-boost for forcefully including blocks. And here, as you can see, those labels, this is the flow for the preconfirmation. So first we register as a preconfer. Then we need to take transaction from the L2 mempool using Taiko proposer. Later we commit to these transactions, and we share information about the confirmations between nodes. And next we want to advance the head of local L2 chain. And after that, we can submit L2 block using block proposed smart contract. And finally, if until the slot of the preconfirm, the block is not included yet, we have to forcefully include it. So we use Mev-boost in this case, not to be slashed. Yeah, and for what we achieved on Helder network, you can see those highlighted labels. Yes, so the development is in progress, and we are able to, for now, to provide those free operations. So we were able to take L2 transactions. We advanced the head of the L2 network, and we submitted a block. And here is the screenshot of the logs from all those modules I mentioned, and let's look into it. This is first our scripts to create some L2 transactions, free transactions in this case, and next one we have logs from Taiko proposer. It just gave us free transactions which we created, and those transactions went to AVS node. These logs come from the AVS nodes, the main piece of software. And what's interesting here is that we, after taking transactions and advancing the head, we just call this proposed new block smart contract at the bottom, and this piece of logs is from Taiko driver, and at the bottom again you can see new L2 block inserted. This is what we achieved on the Helder, so we are able to have it on chain. And this is a screenshot from Block Explorer where we can see this new block proposed transaction executed. Yeah, that's it.
Okay, thanks. Next, I'll give a current where we are and like future directions slide. Can you go to the next slide, please?
Sure.
So the current status is for the smart contract, we've implemented an election mechanism based on an optimistic look-ahead submission design. We also implemented the pre-confirmation disputes for the slashing logic. Right now, we are actively working on ECDSA to BLS mapping design, because like the pre-confirmations will be signed by the ECDSA, but in the look ahead we have BLS, and how do we map them? It's kind of like the active part we're designing. Furthermore, for the AVS node, we are working on implementing the interaction with the existing contracts that we implemented. Also, we're implementing the AVS P2P. For future directions, we are thinking of addressing the fair exchange problem. So we have some ideas, but it's not implemented yet. We want to improve the election mechanism, so we do not rely on an optimistic look-ahead submission. And also, one interesting direction that we're looking into is L2 PBS. So like in the design diagram that we've seen so far, the L2 preconf blocks are built locally by the L1 proposer. But the L1 proposer is not like optimized for building these L2 blocks. So naturally they would want to outsource their block building. And how do we do that? One way that we think that makes sense is that we can piggyback the L1 PBS pipeline and let the L1 PBS pipeline build and preconf L2 blocks. So like split the L1 slot into like several of these rounds or like these sub slots, and run the PBS pipeline multiple times to get the pre-confirmations. So this way you get pricing and you do not introduce any external actors to the system. That's it. Yeah, thanks everyone for listening. Oh, not yet. Okay, sorry. Yes, future reading. First, first and foremost, please take a look at our Taiko POC design doc. It has a lot of the design, especially around the contracts and slashing and look ahead, where we did not discuss in this talk. And strawmanning based pre-confirmation is a research post that I written more about like the negative externalities of the continuous pre-confirmation, and base pre-confirmation with multi-round Mev-boost is about the idea that I talked at the end of piggybacking the L1 PBS pipeline to provide L2 pre-confirmations. Okay, that is it. Yes. Thanks everyone for listening, and yeah, let me know if you have any questions.
Thank you so much. Very interesting to see 3 completely different approaches to pre-confirmations. And one question I have is on Arbitrum being continuous. My understanding is that they have 250 millisecond slot time, so they do batching, but I guess it feels continuous. And so maybe the sweet spot is like somewhere in between, where we have these batches, but still very short slot times.
Okay. Yeah, thanks for the information.
I mean, one thought on batching is that if we have 10,000 TPS, for example, the overhead of dealing with things on a transaction by transaction basis might be too high, and so batching might just be necessary for it to be practical. But one thing that you mentioned is on the searchers, potentially spamming the chain. The way that I think about it is that the gateway has the last look. And so it will basically be adversarially picked by, if the searchers keep spamming, they will always be losing money, because either they're kind of offering a price that the gateway is not willing to sell at, or they're basically sending a stale order that now the gateway can just pick and abuse. And so the way that I think about it is that pre-confirmations is really for users that are willing to pay this UX premium. It's not for searchers, because they will just get picked by the gateway.
Yeah, I think that makes, well, let me think. So yeah, I think, so you're saying that the gateway can filter out these failed transactions, that kind of the...
Well, the gateway is only willing to sell the block space at fair value plus epsilon, where epsilon is like the UX premium, let's say. But the searcher is only willing to buy at fair price minus epsilon. So by default, they won't agree on the price. But if they do agree on the price, it's because the searcher, sent a request, a pre-confirmation request, and now the request is stale, and so now they actually are paying fair price plus epsilon, and so they will be losing money as an arbitrager.
Yeah, I guess so, but I do think that these kind of things are like kind of happening in these low latency blockchains, and then like they are spamming, and I guess the issue is like whether this spamming results in like the user's fee increasing or not. And yeah, as long as that's not happening, maybe the spam is not an issue. Like searchers are just missing out on value and not an issue. But yeah, that I'll be interested in what actually happens.
I mean, as Connor wrote in the chat, the sellers of block space on platforms like Solana are today unsophisticated, and it's kind of interesting because we're probably going to see pre-confirmation tips happen on Solana before they happen on Ethereum, and so we can reuse a lot of the R&D that Solana will have to go through.
Yeah, I completely agree. I think Solana is kind of front running pre-confirmations or base pre-confirmations.
Right.
I just had a quick one. Is MR Mev-boost, is that a fork of Mev-boost?
I think it will be a fork of Mev-boost, but we haven't started implementing anything, so yeah.
I'd be curious if there's something advantage-wise you get over something like commit boost. I'm kind of showing my own book here, but just would be keen to explore that with you guys.
Yeah, definitely.
I think
so. Yeah.
Awesome.
So Justin, in your searcher view, do you see searchers waiting near the end of the block to put in their transactions then? After the user ones are pre-confirmed?
I mean, the way I think about it is that searchers are really only relevant, well, arbitrageurs are only relevant for the very bottom of the block, yeah. So, but that would be outside of the pre-confirmation cycle. It would be as part of the block building cycle at the very end of the slot. And they would be working with builders just like they work with builders today.
And what about like OFAs where like the user transaction is part of the bundle, for example?
Right. So so here I have a new name which I call prices. So we do need to price the pre-confirmation tips, and this is something I've talked about at EthCC. And the basic idea is that the user sends their transaction to the gateway, and then the gateway shares it with various prices, and then the prices are taking on the MEV risk for the gateway. So basically the gateway is always making a profit by giving out a pre-confirmation, and then the various searchers are competing against each other to provide the smallest pre-confirmation tip to the user. So and in addition to that, you know, they would be solvers in the sense that they'd be solving the intent of the user. So yes, there is like this per transaction OFA going on, which simultaneously solves the user's intent and also prices the pre-confirmation tip to be as competitive as possible. And from the perspective of the gateway / proposer, they're guaranteed that they're making money by giving away this pre-confirmation.
So it kind of acts in that sense, kind of like an OFA for it. We're thinking about doing something similar in that sense. That actually could be helpful for some of the pre-conf projects where we have a super builder called Javelin, and we're going to have a gateway for it where users submit their requests to this one RPC, and then you essentially have builders that all compete for it. And because they're all cross-roll transactions, where the builder has to generate the second part of it, because you can't give every single user mint and burn rights for tokens. So you need to have like a list of builders that can move assets across different chains. For this, in this case, they would be able to compete for that. And that was kind of how we were thinking about using an OFA, but they could also compete to get the best pre-conf on different markets as well. So, yeah.
Right, and specifically competing on the pre-conf tip.
Yes.
Right.
So in that setting, then let's say the searcher wins the OFA, then is there bundle pre-conf?
So yeah, the searcher can add their own transactions and that, you know, help fulfilling the intent of the user. So yeah, so long as the user's intent is satisfied, you know, the searcher is allowed to insert their transactions as part of the bundle.
Okay, so then the pre-confs are for searchers too, it sounds like.
Yes, but they're not consumers of pre-confirmations. They're sellers of pre-confirmations. They provide pre-confirmations. Okay, fantastic. Go
so in that case, the searchers are essentially saying, I own X number of block space. I'm going to provide the user the lowest amount possible. So then they could do something like a block space future to price it on the pre-conf side. So the searchers are basically trying to price the most efficient pre-conf possible. And by efficient, I mean lowest price to the user where the searchers still make a profit.
Exactly. So the gateway owns the block space, and then they try and allocate it as efficiently as possible. They want to guarantee a profit for themselves. And then they basically open it up to the market of prices / searchers / solvers, who, as you said, try and provide the best price for users that still gives them an edge. Okay, perfect. Let's move on to the very last demo from Primev. Murat, the floor is yours.
Thanks, Justin. I'm gonna go over a very basic system setting We have a CLI demo. Mev-commit's live on Holsky, so if you want, you can go hands-on and get your own execution pre-confirmations. So Mev-commit places execution pre-confirmations by default. These are on L1. So it's kind of a searcher-oriented or solver-oriented thing. So if you imagine somebody, let's say, using something like MetaMask or a wallet, essentially, they would go through some sort of process like the one that Justin just highlighted, whether it's an OFA or something else. And the pricers or the service providers in that case would use something like Mev-commit to kind of source these commitments, right? So anyone can join using a bidder node. The wallet itself could theoretically, but we don't anticipate that to happen. We anticipate more sophisticated actors to do it. And then they can communicate with providers of execution services. This can be L1, L2, and it's agnostic both to the chain and the actor. But essentially, this provider is able to make the decision on whether they want to commit to an execution of a transaction or a bundle. So it has kind of bundle or mega bundle support. And if you're looking for inclusion or you want to kind of delineate your risk between execution and inclusion, you can add the transaction hashes that are allowed to revert in the bid payload. So what happens is once you send a bid, you receive a commitment from a provider or a set of providers, depending on your setting. And that commitment goes back to the bidder in real time optimistically, but it also goes to the Mev-commit chain, which will then, at settlement time, check for its, whether it was sent in an acceptable time frame, and it will also process things like decay if it was not. So the bid is able to decay, and everything here that you see is basically, fully invisible to anybody else. They would only see a hash up until the settlement time that comes on after the block for which the pre-confirmation is for has been already confirmed on chain. So, and really what happens is to provide the execution pre-confirmation, the provider underneath has to do a series of actions in order to deliver it, right? So in the case of Ethereum, what they would do is run kind of a simulated block with this transaction, and you can name that like Ethereum Prime or something. And then they would essentially build blocks or try to deliver blocks that conform to some version of this transaction executing, right? And they would essentially send that over to the proposer. Whether the proposer does it, Relay does it, block builder does it, doesn't matter. But then that block would make it on chain. And then currently there's an oracle that's implemented that is centralized, but it's becoming an AVS. And we're also working with some proof teams to make this into a full-on proof so that there's no centralized dependency. But today this oracle looks at the L1 block to see whether the commitment was delivered or not, and then rewards or punishes or slashes the providers. So that's generally the setting. What I will now do is show you a brief video of how this works in the CLI. Essentially, you're able to specify a bid. So in here, I'm pasting a bid that I've pre-constructed, but you're able to basically specify, excuse me, which time frame that you want this bid to be valid in through setting these decay start and end timestamps. So you can effectively create your own fill or kill order by making the decay end timestamp very soon, or you can make it at the end of the slot so that you have basically more time for receiving a commitment. So you have this optionality, and the fair exchange problem is solved in the most kind of economically efficient manner in this way, because the chain acts as the coordination agent between the provider and the bidder. So once you send this, you receive a commitment, and there's a digest in there so that you can look at it. I think I made this video when I was in Brussels, and the only provider at that point was in North America. So as you can see, the speed is a little higher than some of the demos that I've seen. But you can co-locate, or as more providers are on there that are geographically distributed, you'd be able to get different latencies. But yeah, everything you need for your pre-confirmation is in this commitment, including some of the details around decays and whatnot. And you can receive also multiple commitments from different actors depending on the setting. So if it's an L1, you'll want all of the registered block builders to commit to you. If you have a marketable price on your pre-confirmation, this should happen because they're rational actors. But in the case where you don't have a marketable price, you might have situations where some block builders do commit and some do not. And then that's gives you some information. Again, these are execution pre-confirmations. So as soon as you have this commitment, you know that your transaction will be executed by that committing provider, which in most L1 cases will be an L1 block builder. Now, the last thing I want to highlight here is essentially, I'm sorry. So we recently had some analysis on some of the bids that were done and some of the execution pre-comps that were delivered. This post I posted yesterday on the group that you can look at. But essentially, there's a number of Holsky blocks in there that are pretty interesting to look at. We're seeing pretty erratic bidding behavior from bidders. This is mostly because, one, there's not much state contention to, testnet ETH is easier to come by than mainnet ETH. But what's really interesting is that there were 807 pre-confirmations that all added to the block value to some degree. So here we're seeing the distribution between priority fees and pre-conf bids in blocks. And it's very interesting to see this distribution. I think people are experimenting with going 50-50 or going all in on their pre-conf bid, depending on their transaction. Our next steps is obviously to bring this to a more closer environment on mainnet, so that we can actually get real data and collect how execution pre-comps work in a state contentious setting. That's mostly it.
Amazing. Thank you, Murat. Any questions? I guess Drew has been asking everyone whether or not Commit Boost is being used. Are you using Commit Boost in any way, or do you have plans to use Commit Boost?
Not on this. The validators that have opted into this are on Holsky, but we do have, we're in touch with the Commit Boost team and the Helder efforts. We have some early efforts on Helder, so as as things progress, we'll have more on there as well. We're agnostic to Mev Boost or Commit Boost, or maybe I guess Mr. Mev Boost. So we're happy to work with all of these. We're compatible. And then we're also thinking of some special modules for something like Commit Boost, but that might be a little bit more medium to long term. Also, for folks who are interested in doing OFAs or are looking at maybe more on the consumer side of things, where the OFA could leverage something like Mev-commit, please reach out to us. We'd love to kind of collaborate on those. And we've developed this chain that has very specific additions around being able to read milliseconds instead of the Ethereum Geth, which is second based, which allows you to kind of launch contracts to kind of help a fair exchange problem that some projects are dealing with. So we'd be very interested in working with you and kind of leveraging the Mev-commit chain to solve it for you. And you can have your own contracts on there and use some of the primitives that are available.
I have a question about the final data that you presented. Like, who are the bidders in this, like, this testnet? Like, I'm interested in like what their intentions are for requiring pre-confirmations in testnet.
Searchers and solvers mostly today. There are a few researchers, but the majority are searchers and solvers that are kind of testing the network, and they have like requirements on how they want the bids expressed, etc. So it's helpful for them to go hands-on and get familiar with how execution pre-comps work on Mev-commit.
I see. Thanks.
Yeah, in the L1 setting, it's the bid expression is at least oriented a little bit more around like bundles. So you can like pass, let's say, 3 transaction hashes, and one of those transactions could be an end user's transaction. Let's say it's a sandwich of some sort, right? In that setting, you could also source the pre-confirmation for the end user too. So you could run some sort of OFA, and the winner of the OFA, or even during the bidding process, could use Mev-commit bids to actually get a price on what that should be and deliver it to the end user.
Murat, thanks again. We're just on time at the hour, so we're going to close off the public part of the conversation and open it up to the private part of the conversation, where anyone's welcome to give us an update or ask a question or bring up a topic that's on their mind.